Alright, let's just get started. Let's dive right in. So today we're going to be talking about quantum computing. It's going to be a gentle introduction, but it's sort of between quotes because there is no gentle introduction to quantum computing, as there is no gentle introduction to quantum mechanics as well. What we're going to try, and most of all, we're going to attempt the impossible, and that is to explain quantum computing without using any sophisticated math. So you do have to know your additions, your multiplication tables, and so forth, but beyond that, we won't require any fancy probabilistic math knowledge and so forth. So, quantum computing. Let's just start out, as all cheesy presentations do, with a small definition. So, this is something that I found on the internet. What is quantum computing? Well, it's a quantum computer exploits properties of quantum physics to perform certain types of calculations more efficiently than any classical computer. It's a definition, but at the same time, it says nothing, right? Because I highlighted a few of these questions. What is quantum physics? What do they mean when they say certain calculations? Which kind of calculations? What do they mean when they say it's more efficient? And most of all, what the hell is a classical computer? Well, we all know what a classical computer is, but what makes it different from a quantum computer? And why would we even need a quantum computer in the first place? Well, first of all, let's take a look at classical computing. So, classical computing, as you might know, works through transistors. So, a transistor is basically a switch. If you press it, a current passes through, which means a 1. If you don't press the switch, no current passes through, which means a 0. So basically, this is what you get. You can use transistors to build a single bit. But it turns out that these transistors are, of course, the basic building block of our current computers today. It turns out that you can combine these transistors and do all sorts of interesting things. So this is what we call an AND gate, which basically passes on a signal if both A and B are equal to 1. This is another basic building block of classical computers. And if you take this building block, you can combine them with other kinds of building blocks and build all kinds of interesting stuff. This is a system that adds two numbers together. And if you have something like that, well, you can then build systems that take this building block and basically make a multiplication building block, and so forth and so forth. So basically, building on top of transistors, we have created ever more complex building blocks that we use today to create computer programs and all the fancy stuff that we see around us. So yeah, this goes all the way to the integrated circuit chips that we see today. So what's the issue, right? Seems like a good plan, seems like something that works quite well for us. If you take a look around you, there's quite a few computers around us. So why would we even want to have a quantum computer? Well, let's go back to the basic building block, the transistor. So currently, in current technology, transistors have a size of about 14 nanometers. Now, this might sound quite abstract, but let's just contrast that with a few things that you might know. So, for example, an HIV virus is already 120 nanometers, and a red blood cell is 7 micrometers. So, red blood cells, I would consider them to be quite tiny, are absolutely huge compared to the single pixel on this image that still represents a transistor. So, we are running up to a fundamental limit. So our transistors are getting smaller and smaller and smaller, and as it turns out, these transistors are starting to experience quantum effects. Let me just go back here to the button pressing issue. If you build your transistor small enough, it's possible that even when the switch is not pressed, certain electrons might just tunnel through and give a 1 value after all. So these days, when Intel is working on new generations of computer chips, they actually have to take into account quantum effects to make sure that electrons are not simply going wherever they please without any kind of transistor there to stop them. So it turns out that we can't exactly go much smaller with classical computers. We're going to try for a few more years, but we're up to a fundamental limit. But at the other hand, you can basically ask yourself the question, aren't our current computers fast enough, right? All we do is open emails, browse Facebook, look at some images, maybe a video from time to time. That's pretty much it, right? What else do we do with computers, and why would we possibly need a faster computer than we have today? Well, the problem lies in the calculations. So there are certain types of calculations that tend to explode quite quickly. Let me show you what I mean by that. So this is a very famous problem in computer science. It's called the traveling salesman problem. It sounds quite simple, right? Imagine that you are a traveling salesman. You want to sell some, I don't know, AI products or something. And in order to do that, you have to visit, let's just say, 20 different locations in Belgium or in the US or in Europe or whatever. So you might think that it's quite easy to then find the shortest route that would bring you to all your required destinations and then back to your initial location. Sounds quite simple, right? Sounds like something that Google Maps or Waze would happily calculate for you. Well, as it turns out, it's not that possible. Because if you have 20 cities that you want to visit, well, calculating so you have 2.43 times 10 to the 18th power of possibilities. And calculating that on an average computer would take about 38 years. So it explodes, right? So if you have one city, one combination, it would take you about half a nanosecond. That's fine. 2 cities, 1 nanosecond. Still good, still going strong. Then it jumps to 3 nanoseconds. That's already fine. 12, then we go into the microseconds, milliseconds, and if we make a jump from 10 to 20, we jump from milliseconds all the way through years. And then if we make another jump from 20 to 30 cities, we see that the amount of time taken is 4.42 times 10 to the 30th power, which is about 6 ages of the universe. So if you are an especially busy traveling salesman, you run up to some fundamental issues that you can no longer find the most efficient route for your destination, for your different destinations. And there's a second very famous problem. Who is familiar with this? It's going to be a bit tight to try and have some interaction here, but let me just explain that to the people who haven't heard of it. So there's this famous parable that says that the Persian Shah or the Chinese emperor, depending on who you ask, once had the inventor of the chessboard at his court, and the emperor or the Shah was so impressed with this chessboard that he asked the inventor for anything that he wanted in this world. He could ask for any one thing, excluding his kingdom, and he would be rewarded with it. And so the humble but very smart chess inventor said, I ask for very little. All I ask is that on the first day you put 1 grain of rice on the first board of this checkerboard. And on the second day you put 2 grains of rice on the second one. 4 grains, 8 grains, and so forth. Each time you double the amount of grains that you can find on a certain board. And the emperor or the Shah thought that was a pretty good deal, right? Because he was looking at the first few squares and he thought like, okay, I can do this real quick, no problem. But there's an issue. Because by the time you reach the last field on the chessboard, you have enough grain to cover the entire earth, land, and water with about 6 meters worth of rice. So that's a problem, you know, it's an exploding problem. It starts out quite simple, but as you move on, it becomes enormously difficult. So there are certain types of calculations that have this same problem, right? And there are even applications that use this phenomenon to perform a certain task. One of them is encryption. So encryption is built on the fact that it is very hard for you to factor a number into prime numbers. What does that mean? Let me explain to you. Any number can be written as a product of prime numbers. So for instance, let me just say 6 is 2 times 3. 12 is 3 times 2 times 2, and so forth. You can do this very easily for small numbers, but for very large numbers, so if I would say to you, what's the prime factorization of 10,255,362? Well, that's a very hard thing to calculate. So factoring a large number into the prime constituents is very hard. But how does encryption work? The other way around is quite easy. To check whether or not a certain collection of prime numbers multiplied equals a certain large number, well, that doesn't take a lot of work at all. You can just multiply these numbers and you're done. So this is how encryption works. It's very hard to crack an encryption code, but if you can decipher it, you can very easily check whether or not you did the right thing or not. So this is how encryption works. The second one is simulation. So simulations are an integral part of our society today. We simulate all sorts of stuff. But there is one field that is particularly stubbornly resisting simulation, and that is chemistry, or rather quantum chemistry. So chemistry is all about quantum mechanics, but simulating these quantum effects in chemical interactions is almost impossible, because every single atom influences all other atoms. So it turns out that, for instance, this is a very famous process used in the creation of artificial fertilizer, which is as you might expect, a very important product in our society today. But we understand almost nothing about this process. And if we want to simulate this interaction, so these are all ribbons of atoms and molecules strung together. If we want to simulate something, well, we are pretty much limited to simulating this structure of 8 atoms. This is the best that we can do currently with our current supercomputers. This is a limit that we cannot surpass, because if we wanted to simulate this entire these two organic molecules interacting, we would need computers that take, I don't know, I think I read somewhere that if you replaced every atom in the universe with a computer that is as fast as our current supercomputers, it would still take you about 100 ages of the universe to perfectly simulate this interaction. So we are very limited in our power to simulate chemical interactions. And a third family of problems is optimization problems. So this is basically what AI is all about. Given a few variables, try to minimize or maximize a function. Let me give you a very simple idea. You have $15 and you can buy oranges at $3 and sell them at $5, and you can buy apples at $2 and sell them at $6 or something like that. What is the optimal amount of apples and oranges to buy in order to get the highest possible return on investment? So this is a very simple problem, but these days we are doing this same task with thousands and thousands and thousands of variables. And increasing this amount of variables also exponentially increases the compute time. By the way, exponentially, that's the term for what happens on the chessboard. So doubling it every time, this is what exponential means. So it exponentially increases the amount of computing time. And we can see that in a very interesting development, because I run an AI company, we see that in the number of variables being used in modern neural networks. So if we look at 2015, this was the ResNet architecture. Well, this took about 20 exaflops to compute and has 60 million parameters. If we move on to the next one, 2016, speech recognition, we already have 300 million parameters and 20 exaflops. And 2017, the neural machine translation network took 100 exaflops of computation with 8,700 million parameters being considered. So this is an evolution that happened over the past 3 years. And it's only increasing ever more exponentially, which means that even for artificial intelligence and machine learning, we are about to hit a fundamental limit. There will come a time when classical computers would have to calculate certain networks for years in order for them to be trained. So this is something that we want to avoid at all costs. So right, I think we now have defined why we need quantum computing, right? On one hand, the speed of our computers are running up to a fundamental limit. And on the other hand, we have certain kinds of problems that simply explode, no matter how fast we make our computers. So enter quantum computers, enter quantum mechanics. Sounds so cool saying it. And let's just start out with the most important fact of quantum mechanics. This is a quote by Richard Feynman, who said that if you think you understand quantum mechanics, you don't understand quantum mechanics. And this is from the guy that pretty much invented the concept of quantum computers as well, and was a very important person in the field of quantum mechanics. So, and this is still true, by the way. The more you learn about quantum mechanics, the weirder it gets and the less you tend to understand. So be warned, if you leave this presentation thinking that, man, I still don't completely understand what's going on, that's normal. I did my best. I can only bring you so far, and the more I explain, the more confused you're going to get. But we're going to try anyway. So quantum mechanics, and especially quantum computing, relies on two concepts that are unique to the quantum world, to quantum mechanics, to small, very small systems that experience these effects. And those are entanglement and superposition. And to explain these two concepts, I want to make use of something, well, possibly the most famous cat in the world, Schrödinger's cat. No cat has been more abused in the history of cats than that one. So it's a famous thought experiment, right, by Schrödinger, who said that, okay, quantum effects, super cool. I understand that you guys are all very excited about it, but let's just think about this, right? Let's build a system that experiences quantum effects. So this is basically, you take one radioactive atom, and when it decays, it triggers basically this elaborate Rube Goldberg machine that kills a cat, right? But the thing is that you cannot predict when a certain atom is going to degrade or not. So whether or not the cat is going to be killed. So if you put a cat in a box together with this system and you close the box, then until you look, it is actually in a superposition of two states. It is actually both alive and dead at the same time. Because in quantum mechanics, as long as you don't look at a quantum system, it sort of behaves in two ways at the same time as well. So if you were to build a system that relies on the fact that your atom has degraded, has become radioactive or not, you would see that when you measure that system, you would actually see the two effects at the same time. This is what quantum mechanics is. Two things can happen at the same time, and this is what is called superposition. We'll explain that concept a little bit more. But entanglement is another important one, and this basically means is that you can, the word says it all, you can entangle two systems so that when something happens in system A, it automatically happens to system B as well. And this was basically the core of Schrödinger's cat's thinking. Like, okay, quantum effects in small atoms, everybody, well, it's mind-blowing, but everybody's like, okay, sure, fine. If an atom can be both alive and dead, sure, we don't have any problems with that. But it turns out that you can entangle an entire cat with the state of the single atom, and so then we translate the problem into something much bigger. And if you ask somebody, can a cat be both alive and dead at the same time? Well, then yeah, the answer is obviously no, right? So this was the origin of this thought experiment. But as it turns out, the thought experiment was meant to show how absurd quantum mechanics is. Well, it turns out that quantum mechanics is 100% right. We haven't done this experiment in reality, by the way. We haven't put any cats in boxes, just to be sure. But if we did, well, there would be some fundamental problems as well. But if we did, we would actually see, if we could measure the aliveness of the cat, we would measure that it is, on average, 50% alive. Quite strange. So then what is quantum computing, right? So quantum computing uses two phenomena from quantum mechanics, entanglement and superposition, and it uses that to create something that can calculate. But what does that mean? So in classical computing, the basic unit of computation is the bit. And a bit can be either 0 or 1. Easy. In quantum computing, we have qubits, very aptly named. And the thing about qubits is that they can be both 1 and 0 at the same time. Or 0 or 1 or any possible combination of these states. But the thing is, when you look at them, when you measure them, they will take instantaneously one of two possible values. So this is what is important about the qubit. As long as you don't measure it, it's both things at the same time. And the moment you look, it will take one of two possible states. Let's take a small metaphor in order to visualize this a little bit better. So superposition, right? Look at this structure. So I actually forgot what it's called. It's a cube, Penrose cube or something like that. Look at this cube. And then look at these two images. If you concentrate, you can sort of make the cube pop out or pop in, depending on the way that you look. But until you have seen these two things, it's actually both at the same time. It's only when you look and focus that this cube will take one of two possible forms. This is what we call superposition. And then to demonstrate entanglement, try and envision the left cube in the 0 configuration and the right cube in the 1 configuration. It's almost impossible. As soon as you put the left cube in a certain configuration, the other one will take the same thing. It's part of the optical illusion. So this is what entanglement means. It says that when you look at the left cube, the right cube is entangled with the state of the left cube. This is entanglement. And turns out we can do some interesting things with that. So if we start to combine qubits, we can actually build systems that can analyze all possible configurations of these bits. So if we have a classical computing system, we would see that it has only one state. For instance, 000000000000001, all the way to 11111111111, and so forth. But it can only be one possible configuration at the same time. In quantum computing, if you have a computer program, you can actually feed in all possible permutations of the input at the same time. And that is what makes quantum computing quite special. And we can use this phenomenon to build circuits, quantum circuits. So this is a Hadamard gate. This transforms a regular bit into a qubit. This is what's called a control not operator. I actually forgot what this one is, but it's all part, it's actually quite similar to the gates that we saw at the beginning of this presentation, the AND gates, the OR gates, and so forth. And what is quite interesting, so instead of having to basically iterate all possible inputs through a certain gate and see the results, you can actually put them all through them at once. But then the problem is that it will also give you all possible outputs at once. So try and imagine it like this. This is an intuitive approach towards quantum computing. So imagine that you have an entire room full of workers. And you go to the workers and you say, okay, I got a problem. You, number one, you work on this problem with input state number 1. You work on the same problem with input state number 2. Everybody start working, and when you find the answer, just shout it. And then at the end, everybody will start calculating all possible permutations of the input at once. And then at the end, everybody will shout their answer. 8, 2, 5, 16, and so forth. Everybody all at once. So the problem is that when you want to find one possible answer out of all the possible answers, it's quite hard, because it's drowned out by the noise of all the other answers as well. This is a fundamental problem in quantum computing, and this also means that a quantum computer is not a universal computer. You cannot, you will not be able to play, I don't know, Fortnite or Minecraft on a quantum computer. It can only do certain tasks, and you need to design your programs very cleverly to actually have them work on a quantum computer. You need to build a circuit that dampens your wrong answers and amplifies the right responses. So let's just say that you could go to your room full of workers and then say that, okay, the larger the number you found, the larger you have to, the louder you have to yell. If you found a small number, you can whisper. If you found a large number, just yell it out. So this would be a way to get a correct answer from a quantum system, because you can then simply listen for the loudest signal that you can hear. This is how quantum circuits work. It's a lot more complex than that, but if I go any deeper, my mind will be blown and yours will probably as well. So for instance, let's take a look at prime factorization. Let's go back to that, because that is the most, probably the most famous application of quantum computing, right? Encryption. Encryption will be totally destroyed by quantum computers, because quantum computers can do prime factorization quite easily. So let's take a look at a graph. It looks hugely complex, but basically, let's just say that you have to factor a prime number, and this is the number of bits that your prime number is made of. If we use a classical computer, we see that below 100 bits, it doesn't even register. It takes you less than 1 nanosecond. It's no problem at all. But as the problem size increases, we see that in a classical computer, the amount of years that you would have to calculate jump between 800 and 1,000 from, I don't know, 1 million years to more than 1 billion years. So as we move on, it quickly goes into ages of the universe of calculation. So it's a fundamental limit, and by the way, this is, I think, what are we now? 2048 bits is the recommended key length, and it would take you about 6 ages of the universe to calculate. In quantum computers, the graph looks quite different. But there's a subtle fact that very few people will talk about when we are talking about quantum computers, and that is that we have no idea how fast these quantum computers will actually calculate. We have no idea what the clock rate of a quantum computer, what the maximum clock rate of a quantum computer is going to be. Different approaches have different speeds. So you could build a very slow quantum computer that does 1 operation per second, 1 hertz. But then you see that in the beginning, well, it would take it 1 month to factor a 3-number prime, which is crazy. It would take a hugely long time. But as we increase it, we will see that it quite quickly surpasses, and it's an enormous speed, it quite quickly surpasses the classical approach compared to the quantum approach. And if we were to be able to build faster architectures, we would see that this drops even more. But it is mainly, what I want you to look at is the shape of the line between quantum and classical computing. So this is an exponential curve. It goes all the way up. This is a linear curve, so it only increases linearly. You can double the amount of bits, and it will only take you 2 times the amount of computation compared to, I don't know, a lot of multiplications. So what does it mean in practice, right? Where are we now with quantum computing? So first of all, this is a quote by Jim Clark, the director of quantum hardware at Intel. You can read it all if you want, but basically it boils down to this. Right now, if we were to compare the current state of quantum computing with classical computing, we would see that we are now in the 1950s. We don't even have the transistor yet. We're just building some circuits. Maybe we can do some cool toy examples like I don't know, yeah, we don't have any Nazis to break encryption these days. But we could do some small things that were quite interesting. But yeah, we're simply not at the point that we can do any type of practical applications. But that's quite normal. In 1958, we were at the same point. In 1971, each of these milestones was a decade apart. So 1958 was the first microprocessor. No, the first microprocessor was in 1971, and the first transistor in 1947, and integrated circuit in 1958. I didn't even read the quote myself. But yeah, so right now we are at a handful of qubits. But very quickly, this is increasing, and we hope that there would be something like a Moore's law for quantum computers as well, that would bring us every year twice the amount of qubits, which would be unimaginably huge. So let's take a look. So right now, the largest systems, I think that it's actually IBM that has the current record, right, like 50 qubits for a classical, for a universal quantum computer, quite important. So 50 qubits, but they are quite noisy. So let's say that in practice we have about 5 or something. So we're at 5 now. If we want to take a serious stab at simulating the process behind artificial fertilizer, we would need about 100 to 200 logical qubits. Carbon capture is the same thing. We could build systems that capture CO2 from the air more efficiently than we can do right now. Material science is quite similar. It goes from 100s to 1000s of qubits. We could simulate materials without ever actually having to build them, which would be huge for construction and energy and stuff like that. And then finally, but this is still quite blurry, literally and figuratively as well, comes machine learning. So there is a suspicion, that's all we can say right now. There is a suspicion that quantum computers would actually be better at machine learning, exponentially better at machine learning than regular computers. So this would mean the world to artificial intelligence as well. So if I had to make a personal prediction, I'm gonna say that in 10 years, AI research is going to drop off because we are running up to some fundamental limits. But then, so then we will go into another AI winter of about 10 years, and then quantum computers will arrive on the scene, and then suddenly we will see huge machine learning models being trained on quantum computing. So quantum computing has the potential to become an enormous accelerator for artificial intelligence, besides meaning a total revolution in every industry from construction to pharmacy to chemistry and so forth. So yeah, just to illustrate, if we take a look at factorizing prime numbers, we see that a Shor's algorithm, so a quantum algorithm, has a huge increase in speed and efficiency. Searching an unstructured database is also quite interesting, but for machine learning, we're not quite sure. It's quite possible that there is some optimum point at which quantum computers become more efficient than classical computers, but we're just not sure yet. We think it might be, we suspect it might be more efficient, but we have no idea for that. And there's another important factor, 10 minutes, great. There's another important factor that very few people will talk about. So especially when large tech companies build new quantum computers, they will only communicate one thing, and that is the amount of qubits. This is what's being fought over right now. But what nobody talks about is the error rate. And the error rate is, if possibly, more important than the amount of qubits in a system. Because what is really important is the quantum volume, the amount of calculations that you can actually perform. Take a look at it like this. You could have a system with millions of qubits, but if they are wrong 50% of the time, well, they're simply doing random stuff, and you can't use them at all. So you can increase the amount of qubits, but beyond a certain point, if you have a very high error rate, and this is like 0.1% or something, if you have a high error rate, you will see that if you increase the number of qubits from 100 to 200, you will actually not have an increase in the amount of computation that you can actually do. But what is really important, if we were to move from an error rate of 0.001 to 0.001, we would see that decreasing the error rate by 10 increases the quantum volume by 24 times. So this is actually something that quantum computing is only now sort of becoming aware of. So we just managed to build quantum computers with multiple qubits, but now we're like, oh shit, if we do any more, we won't be able to do any meaningful calculation with it. So we need to decrease that error rate as well. And so for the longest time, people were actually convinced that quantum computers, practical quantum computers, were impossible. Because, yeah, there were no straightforward ways to reduce those errors being put forth by quantum systems. But luckily, we found a way. But to be fair, it sort of sucks, right? Because what we can do is actually use multiple physical qubits and then sort of, let's just keep it simple, average them together to create one logical qubit that has a much lower error rate. So think of it as an error-correcting code. Let's just say that I want to transmit one single bit to you and it has a 10% chance of doing something wrong. Well, if I send one bit, a 0 or 1, it has a 10% chance of flipping. But if I would send 3 bits, let's say 111 for 1 and 000 for 1, if you then get a message that says 001, well, you can be reasonably confident that the actual message is a 0, because the chance that 2 bits are flipped is way higher than the chance that 1 bit is being flipped. So this is basically the brute force approach towards building practical quantum computers. Basically, make a system that has a huge amount of qubits and then sort of bundle them together to create logical qubits. It's great, but it sucks at the same time, because the physical to logical ratios might be as high as 10,000 to 1 for some technologies. So imagine that we now have 50 qubits and we're like, yes, we're almost there, we're doing it. But it could be that when we reach 10,000, we can now confidently say, and now we have created one good qubit, which would be, yeah, sort of disappointing, right? And this is actually the main thing that is determining sort of the Moore's law for quantum computing right now. So if we take a look, if we end up with a logical system with a 1,000 to 1 ratio between physical and logical qubits, you will see that it will take about until, let's say, 2028 before we can sort of build systems that are better than classical computers at certain tasks. It will take until 2030 before quantum chemistry starts to become possible on quantum computers. But if we were to upgrade that to a 10 to 1 ratio, well, we're already at machine learning, which is a hugely complex task, by 2025. So, reducing the amount of errors in quantum calculations is the main focus of research, well, not the main focus, is a very important focus of research into quantum computing right now. You might, if you're a very fast reader, you might be sort of confused by this entry here, by D-Wave. who claim that they have systems with 4,096 qubits, but D-Wave is sort of like a strange exception. They do not build universal quantum computers. So they actually build systems that can do less calculations than an actual quantum computer. They can only do one thing very well, which is optimization problems, which would be huge, by the way, don't get me wrong. There's a reason that Google invested several billions into that company. They are very promising. But most people are still looking forward more to the universal quantum computers. And another thing to realize is that right now we don't even yet know how we are going to build these quantum computers. There are several competing technologies. I'm not going to go over them all, but the thing that you need to know is that any system that shows quantum properties can be used as the basis of a quantum computer. So they have superconducting loops, they have trapped ions, quantum dots. This is amazing. This is what Microsoft is working on, topological qubits. They actually create artificial qubits that don't really exist, but exist through interaction between classical systems. It's crazy stuff, all the way up to diamond vacancies, which is a very, very, very experimental technology right now. This is currently superconducting loops. This is currently the one that is being worked on the most. Also, because it plugs in to the existing semiconductor industry quite efficiently. So we don't have to build new infrastructure. We can pretty much reuse the stuff that we're already using to build classical computers. So if we take a look at the established companies, we have D-Wave building their own specialized version of quantum computers. Then at the very top right now we have IBM, which has taken a huge leap in the amount of quantum bits that they offer. And they even offer a public quantum computer that everybody can use. So if you go to the IBM Q Experience, that's the right one. The IBM Q Experience, you can actually just from your browser create a program that will run on an actual quantum computer. It's crazy stuff. So they are working quite hard on making the knowledge of quantum computing available to the broader world. But of course, Google, Microsoft, and Intel can be far behind. Google is investigating multiple technologies, are investing in pretty much every startup that has something to do with quantum computing. This is, by the way, the universal rule of Silicon Valley. If you can't build it yourself, just buy another company. And there are also some very interesting startups as well. IonQ is something that I am especially interested in because they are working on trapped ions for their qubits, which would mean that they have a very stable system for computation. The only downside is that they need actual physical lasers to manipulate the quantum states, but that's out of scope for this presentation. And just to really drive the point home that quantum computing is going to be super important in the future, even the European Union is already on board. So I would expect them to sort of realize that quantum computers are going to be big by the time they've already been quite established. But even Europe is investing $1 billion into quantum industries. But just to put a little bit of context behind that, the US is investing $1.2 billion and China is investing 10. So take from that what you want. Where are we going with this? Well, what is the future of quantum computing? Are you going to have a quantum computer on your desk? Probably not. So where we are probably going with this is that in the future you will have quantum as a service. So there will be large data centers that basically have one supercomputer that's being shared among all other people to perform certain types of quantum calculations. Of course, this is basically the same thing as the chairman of IBM saying that there is a world market for about 3 to 5 computers. We don't know. Maybe we build a very efficient quantum system that fits on the chip and it will be part of every smartphone. We don't know. But as it's starting to look right now, because these quantum computers require absolute zero temperatures in order to function, they require complex cooling systems and so forth, they will probably, especially in the near future, only be available in specialized data centers. All right, that's the last part of my presentation. I wanted to take this final slide to point you guys to a very interesting website, www.qntm.be. This is actually an initiative that we have started as well with the Raccoons group around quantum computing. So feel free to have a look. We even have a Slack community where I post all kinds of interesting, well, not only me, all kinds of people are posting interesting articles that they find on quantum computing. Okay, that's pretty much it for me. Thank you for your attention, and now I have to get going.